Right, so, okay, so let me just remind you of some classical geometric measure theory. That will be the start of the talk. So, right, let's recall, let me just recall the following. So if E in Euclidean space is n rectifiable with finite Hausdorff measure, then the area formula implies that the Hausdorff densities of E exist almost everywhere. So this is the limit of the measure of balls divided by the corresponding measure of the Euclidean ball. Right, this equals 1 almost everywhere. Okay, so this is just area formula, and if mu is an n rectifiable measure, meaning it's absolutely continuous with respect to Hausdorff measure with restricted to a rectifiable set, and just for simplicity, I'm going to suppose that all measures are finite on bounded sets. Right, so if mu is n rectifiable, then the Radon-Nikodym theorem combined with this implies that the density of the measure, right? So that's why I wrote this funny way around. This also exists and is positive and finite. Mu almost everywhere. Okay, and so one of the oldest questions in geometric measure theory is, what about the converse? So, you know, the kind of one of the questions that started this whole business off was, or one of the answers due to Bate in 37. Well, he only worked in the plane, but his proof works in any Euclidean space. It says that if the one-dimensional density exists and is positive and finite, mu almost everywhere, then mu is rectifiable, is one rectifiable. And of course, the higher dimensional questions were a famous open problem. There's a partial result in between due to Marstrand in 61 for dimension 2 and Matula for the higher dimensions in, I think, 75, which says that if the Hausdorff density of Hausdorff measure restricted to a set, if this equals 1 almost everywhere, then the set is rectifiable. Right, and then, of course, finally, there was Price in 89, who solved everything completely, which says that if theta n mu of x exists and is positive and finite, mu almost everywhere, then mu is n rectifiable. Okay, so the question that I want to talk about today is what happens in non-Euclidean geometries. So what happens if we replace Rm with something else? Okay, so right, first off, this makes sense, right? Density just depends on a measure and a ball, so this makes sense in any metric space. Okay, and Rectifiable, you just have to tweak the definition slightly. So E in X is n rectifiable. If rather than covering by Lipschitz images of Euclidean space, we cover by subsets, right? So if there exists subsets of Rn and Lipschitz maps to X that cover almost everything, okay, so we at least have questions that make sense. And I should just say, this isn't just, this is even an interesting question in Euclidean space. I mean, with Rn equipped with a different norm, right? If we equip Rn with a different norm, then this corresponds to taking densities with respect to a different convex set, right? So these are densities with respect to Euclidean balls. You may equally wonder what happens if you take densities with respect to squares, right? And that would correspond to taking the supremum norm on Euclidean space. The motivating question, so the area formula holds, Radon-Nikodym theorem, of course, holds. So it's true in any generality. If mu is n-rectifiable, then the density exists and is positive and finite mu almost everywhere. Okay, so again, we're interested in the other direction, right? So, of course, the first question to ask yourself whenever you want to do this is, well, do these guys tell us anything, right? These proofs are extremely clever, so maybe they tell us something, and indeed they do, right? So Besikovich's proof works in enormous generality. Right, I will give a sketch of the main idea in a moment. The key point is that it requires balls that are sufficiently strictly convex, right? So it only requires balls in X to be sufficiently strictly convex. Okay, I rather than define what I mean by this, I will just give you some examples. The proof works in any strictly convex, for any strictly convex norm. So if we have Rm with a strictly convex norm, right? It also holds in something called the Heisenberg group, with, so those, I'm not going to define what this is, but basically this proof works with any norm that has convex balls, like strictly convex balls. So for example, with either the Korani norm or the CC metric works, but it fails completely in the plane with the infinity norm. Okay. A similar story holds for the Marstrand proof. So Marstrand's proof works for any strictly convex norm. I haven't checked the details, but I would suspect it probably works in these spaces. But again, it completely fails for the infinity norm. There's very, very hard partial work by Andrew Laurent that proves something in this direction, but he can't get, he doesn't get to rectifiability. And then the Price proof does not work in any generality except for Euclidean space, right? So it really requires an inner product. So it requires Euclidean balls. For strictly convex, for other norms, essentially nothing is known except for a few trivial things. But it really, nothing is known. It's not even clear if the exponent has to be an integer in this case for whenever the space is not Euclidean, right? So Marstrand's theorem, what's known as Marstrand's theorem in Mattila's book, is not even clear to be true. But there is one consequence of the statement of price, is that if you allow yourself to work in just arbitrary metric spaces, it's trivial to see that Price's theorem is false, right? So the statement is false in arbitrary metric spaces. So for example, for any alpha bigger than 1, you can consider the metric space R equipped with the norm given by taking an alpha root, right? Then Lebesgue measure is alpha uniform right? So meaning it satisfies something even stronger than the density existing. In fact, the measure of every ball, so for any x and any radius, the measure of a ball of radius r is some constant times r to the alpha, right? So certainly the density exists, and it's, I mean, something much more general holds, right? But this space is purely one unrectifiable. So, so nothing like the Price theorem is true in this generality, right? Except there is just this one tiny gap that we can actually talk about, which is what I'll talk about today, right? This is a counterexample, but only, it doesn't give a counterexample to one uniformity, right? Because for alpha is 1, this is just R, and so it is rectifiable, right? So that this easy counterexample fails for alpha is equal to 1, right? So that, and when we look back at Besikovic, right, I see it works in lots of generality, but it doesn't work in this, you know, case that one would hope to be able to answer if you are prepared to talk about metric spaces, right? So the starting question that I want to talk about today is one uniform metric measure space right? So this is to say a metric space equipped with some Borel measure mu. So we then the fact that it's one uniform would mean that the measure is equal to, well, let's just drop the constant. The measure of every ball is equal to R. Isometric to R. Oops. Okay, and there's reasons why one may believe this to be true, right? Or at least there is, you could be hopeful and expect this to be true, because one-dimensional sets usually are much nicer to deal with than higher dimensional sets, right? And often, if that's due to the following proposition, right? So in general, the theory of one-dimensional sets is simpler due to this proposition, which is that if X is compact, has finite Hausdorff measure, and is connected, then it's a Lipschitz curve. Okay, and you can show it's rather straightforward that if it has a uniform measure, then in fact, this is an isometric to an interval, right? Or it's locally isometric to an interval, right? If it supports a uniform measure, it is locally isometric to an interval. Right, what you have to rule out, basically, you can't have branch points because there would be too much measure at the center of the branch point, right? You would have to R. Did I say? Oh yeah, this is a question mark, sorry. I don't know if that's better. I hope it is. Right, so due to this proposition, basically we reduce the problem to showing connectedness. We don't have to worry about anything more sophisticated than aiming for connectedness. Right. But I will kill the suspense already. This is false, right? This question is false. And I'll demonstrate in a second. Up to isometry in both the metric and the measure, so scaled isometry. There exists 3 one-uniform spaces. Of course, there is R. And there's 2 others. Rather than just give you the definition now, I will try to sketch the proof of why they are the only 3, and you'll see that the definition drops out of the bottom. Okay. Is everything? Are there any questions? Yes. That didn't work very well. Right. So we'll start with sort of the same idea that Besikovic had. So we have, if we want to find something that's not isometric to R, we need to think of a disconnected set, right? So suppose we can write X as a union of 2 pieces that are disconnected, right? 2 closed disjoint subsets, right? Then with not so much work, you can actually find a minimizer of the distance between the 2, and it must be positive, right? The uniform condition means that these spaces are locally compact, so we can actually find minimizers of the distances. So we can show there exists A in A, B in B, such that the distance between the 2 is, let's say, D, which is the inf of the distances. Right, so we have this picture. Oh, and so I will just point out that this obviously implies that for any x in A and for any y in B, the distance from x to y is at least as big as D. Right, so we have the following picture. And then all of the rest of the set lies on this side or on this side. Right. So now I'll just I'll give you the main idea in Besicovic's proof, and you see why A, it just relies on convexity, and B, why if you don't have convexity, then you're in trouble. Right. So let's imagine we start inflating balls around A. Up to distance, up to radius D, I know that I pick up measure linearly on this side, right? But as soon as I hit radius D, oh, sorry, the same thing happens on this side, right? So I start picking up measure D, up to scale D. And now, as soon as I tip just over distance D, the ball around A will start picking up the measure here. Right. So if I just draw this ball just like this. Okay, so now if you do this slightly cleverly, right? So remember, at the minute we have Euclidean balls. If I take a ball of radius slightly larger than how much this sticks out, right? If I look at the measure of the small ball, let's say that this ball is of radius 2 epsilon. So that means the radius of this big ball is D plus epsilon. If you do just the estimates that you get from being a uniform measure, you know that there must be a point in this bit that sticks out. Okay, just because the measure of this ball is 2 epsilon, the measure of this ball is D plus epsilon, and the difference is this thing. So it tells you that actually, because you have this gap in the center, you can put measure epsilon in this bit that's poking out. But now, as you reduce the radius of this ball, you see, if we draw it slightly differently, hang on, how did I? As you let epsilon go to 0, what you actually do is you force measure to lie along this line. Right? If I let me think. If I make the small ball ever so slightly stick out in front of the big ball, I will get a point here, right? And so if you do this carefully, you can make a line segment of length D appear here. But this contradicts uniformity because if you take this ball and this ball, they have the same radius, but obviously this guy has much more measure than this one because this is just half an interval and this is a full interval. Okay, and that's how Besicovich gets his contradiction. But for us, this doesn't work because we don't have a convex ball, right? Like I said, it fails if we have the infinity norm, and you can see straight away why it fails because this big ball looks like this, and the small ball that just slightly sticks out is this other square. And no matter how small you make the smaller radius, you don't get something that just slightly sticks out here. It's the whole side of a square, right? And so this argument doesn't work. Right. So what can we do? Well, let's still try with this type of idea. So again, we have A, B, they're separated by d. So again, as I increase the, so now we work in arbitrary generality. Up to radius d, I know that I keep picking up measure, right? And over here, the same is true. So if I now consider a ball around A of radius r for r bigger than d, I know that you just by the triangle inequality, right? I will start picking up measure around this guy, right? So but the amount of measure that this provides is precisely the amount that this thing needs, right? So I get up to radius d, I need to continue increasing, but I just increase linearly, and that's provided by this point. The small balls around this point provide all of the measure I need, which means that over this side, there cannot be anything, right? Because if there was a single point, it would provide me with too much measure for the measure of the ball. So this says that, and this argument works for everything up to this distance here. So this tells you that for up to radius d, you have this annulus where there's nothing on this side, right? And by symmetry, you get the same thing around here. Okay, so this is empty. And now the last observation to make is the following. Let's suppose I pick a point x that's in this. Oh, sorry. So yeah, let me write down what I formally mean by this. I mean that if you take the ball around A of radius 2d, then this is just the ball around A of radius d union the ball around B of radius d. Right. So now let's take this other point x. What can I say about a ball around x of radius d? Well, possibly it could look like this, where I mean it doesn't take up all of this ball, right? But then it can't eat anything from over here. So that means I would not have enough measure. So what it says is that actually this ball of radius d around x must be all of this ball, right? So for any x, the ball around x of radius d equals the ball around A of radius d. So now if I increase the radius ever so slightly, I need to pick up some measure. There's nowhere over here for it to pick it up from, right? Because I've already taken everything I can. So that means it must start taking up measure from here. So if you consider the ball of radius x, this must pick up measure from this bit. You know that there exists a y in the right-hand bit that has distance equal to d. And it has to be unique too, because if there's another one, I would grow measure twice as fast. Right, so let's define iota of x to be y. By symmetry, you can go the other way around, right? You can map, everything in here has a unique closest point at distance d. What you can show is that this is an isometry. It squares to the identity. And moreover, the distance for any x in the left-hand bit and any y in the right-hand bit, the distance is you equal the triangle inequality across the gap, right? So the distance between x to y is equal to the distance from x to its copy plus the distance from the copy to y, right? So there's this, basically, if you want to go from here to here, you jump to its isometric copy, and then you just take the distance in the right-hand side. Okay, so I hope this is still, that you can still follow this. The last step of the construction, which I guess I will just say over here, is that you can then repeat this. I think I'm doing this wrong. Okay, that didn't seem to work. Right, we then repeat. Right, because if you look at a ball of radius 2d around A, right, there must be some point y primed at distance is equal to 2d, right? Just because there has to be a point that satisfies this because of measure, right? And because of the moat that we built beforehand of radius d, right? These 2 points satisfy the hypothesis that we started off with, but with d replaced by 2d, right? And x and y primed satisfy the starting hypothesis. With d replaced by 2d. Okay, so of course this can be repeated. Okay, so let me just be a bit more explicit now. So this is kind of like some machinery that will construct the spaces for us. So the question that we ask ourselves now is there some ball that is connected? So question is, does there exist a d positive such that the ball around some point A of radius d is connected? Right? If yes, then by the proposition that I write down, it's locally isometric to an interval. So consider a maximal interval that is connected. This is uniform except at the endpoints. So what you show is that, well, if this whole thing has to be uniform, then it must be that the endpoints are actually identified. Right? This is locally uniform except at the endpoints. Which implies that it must be that the endpoints are identified, right? And so this tells you that this ball is isometric to a flat circle, let's say, so it's R quotiented by 2dz, right? A flat circle. Right, so here it is. Here's the flat circle. And now I play the game that I get from this construction. I know that there's an isometric copy such that the distance across the copy is additive, right? If I want to go from here to here, I travel up and then I travel across. And now I repeat at the next scale. Well, this thing has an isometric copy down here. And if I want to travel between the two, I jump to the isometric copies, travel to where I want to travel, and then jump to the isometric copies. Right, and again, you do this at double the distance. This is what I call T. The other option is, what if there's no ball that's connected? So you're disconnected all the way down. You essentially get the same picture, but you allow the radii of these balls to go to 0. Right, and you get the set S, which if just for a formula, you can write down as all binary sequences infinite in both directions that are 0 for sufficiently large I. And you equip it with the metric two to the I. Okay. This is just simply what comes out of this argument of doubling the scales and joining the pieces by additivity, right? That's exactly what this metric comes out as. So at the moment, I haven't proven that these are uniform. I've just shown that these are the only options for being uniform, but it's just an exercise to show that Hausdorff measure on one of these is uniform. Okay, so right, the theorem is that there's R, S, and T. They're the only uniform spaces. Right. So I'll just give some remarks before I go back to the original question of the densities. So this space S, it's quite easy to see that because of how the metric is defined, right, by being this, you take the paths between the pieces, this is actually a subset of L1. Isometrically, it's a subset of L1, but it cannot be isometrically embedded in any locally compact geodesic metric space. Right, so in particular, finite dimensional normed vector spaces. So it doesn't embed into the plane with the square norm, right? So that answers that question. And also, this cannot be isometrically embedded into the Heisenberg group with any homogeneous norm. Okay, I think that's all the remarks. Yeah. Okay. So, right, the reason why I point that out is, of course, it means in any one of those spaces, the only uniform subsets are isometric copies of lines. Right. So in the last few minutes, I'll talk about the original question about densities. I'm sure it won't be a surprise to some of you that we take tangents. Because, well, why wouldn't we? Right? There's just the question of how to define a tangent. So returning to the density. So suppose we have a metric space where the one-dimensional density exists and is positive and finite mu almost everywhere. Right now, you can define, you can take tangents of a metric space. I don't have time to define how you do that, but you take We'll consider tangent spaces. Okay, tangent spaces are defined in more generality than just this. In fact, for any asymptotically doubling measure on any metric space, you can take a tangent. The three important names in this are, of course, Gromov, Prokhorov, and Price. Basically, you consider Gromov embeddings of a metric space, use Prokhorov's theorem to find a convergent subsequence of measures, and then you use Price's definition of what a tangent measure is. Right, and by combining these theorems, as long as you pass to a subsequence, then you know that this always converges to some metric space equipped with some measure. Right, if the measure you start off with is one regular, meaning that the density exists almost everywhere, implies that every tangent measure every tangent space is one uniform. Right, so it has to be one of the three guys that we've already discussed, but there's 2 points. The one with the little circles, T, this cannot be a tangent measure. Right, this is kind of like a very easy version of Price's statement that flat at infinity implies flat. Right? And the second point is that the tangent space is connected. Okay, so if we look at the set of all one uniform space, the space of one uniform spaces, on the right-hand side we have R. In the middle we have the T's with lambda in R, lambda bigger than 0. Right, and as lambda converges to infinity, this thing converges to R. That corresponds to zooming into one of the circles, right? So you can imagine, as you zoom into one of those circles, of course, you see something that looks more and more flat. As lambda converges to 0, you zoom out and you converge to some multiple of the other guy. Right, so the tangent space has to be a connected subset of this space, and it doesn't contain the middle. So this means that tan is either R or it's equal to TS. This decomposes X. This bit is necessarily purely unrectifiable because it can't be rectifiable. If it were rectifiable, then its tangents would be R, which it isn't by definition. So this bit is one purely unrectifiable. The hard part is showing that this bit is rectifiable. Okay, this is actually true in general. If you have a measure, a metric space, and all of the tangents are flat, then it's rectifiable, but that's quite a hard theorem. The special case of dimension 1, the special case of dimension 1 is much simpler, and in fact, it's essentially the same proof as what Besikovic gave in the very first theorem that I wrote on the board, right? So I think I should probably stop there. So thank you very much for your attention.